So hello to everybody, the microphone is active, so let us go to the lecture of today. The lecture of today is called Gauss-Green because we are going to study the Gauss-Green theorem, and the main idea of the Gauss-Green theorem is the following, or just Green theorem. So we'll call it Green's theorem. I like it more. So Green theorem, or Gauss-Green, links the circulation of a very important planar field. So we are in dimension 2. To an integral in the plane, in a planar domain. Okay, I will explain it better, but the first important message is that Gauss-Green holds in dimension 2. Okay? This lecture is about planar fields. Everything happens in the plane. So this is the first important message. We will have a generalization to three-dimensional situations, so fields and domains, will be called the Stokes theorem. Okay, and we will study it in some lecture. Okay, so the situation is the following: we have a plane, and in the plane we have a domain D which has to be somewhat regular. So first, let me first specify something about the domain in which we will work. Okay, so the domain involved by Gauss-Green must possess some regularity features. Regularity. And so, for instance, it must be bounded. This is very important. And it must have a smooth boundary, so to say. So its boundary must be a regular curve or a union of regular curves. Okay? And moreover, most important, the boundary of the domain must be, the mathematical term is positively oriented. What does it mean? It means oriented in the counterclockwise sense. Okay, let me clarify this first point, the first important message, the second important message if you want, with a drawing. And the drawing is the following. So we have a curve, we start from a curve, and the curve must be closed in order to isolate a good domain. So this is the curve that we have in mind. Let me call it gamma. And so let me recall a result, which is a quite deep result. So natural. This is a natural but deep and difficult result. This is called the closed curve theorem, which says that a closed curve, so namely what we call a circuit, splits the plane in two regions. The so-called interior part and the external part. Yep. Okay, this is quite logical if you want, because for instance here, what we have here is that the internal part of the curve or the interior part of the curve is this. Okay, I don't want to give a perfect picture, but this is the internal part. And the external part, of course, is what is outside the curve. This is very natural. It is somewhat childish, if you want, but you won't believe how much the proof of this result is difficult. There are no simple proof of that, no elementary proof of that. Many mathematicians are looking for that, but there are no simple proofs. Okay? So, this is the first point, okay? First point. The second point I want to stress is the following. It's about the orientation of the curve. So, intuitively, a curve is said to be positively oriented if when running through the curve, the representative point always has the internal part of the curve to its left hand side. Okay, this is somewhat strange to be said, but in order to understand it, think of gamma of t, so a parameterization, gamma of t, which is some x of t and y of t. So remember that when you parameterize a curve, morally what you are doing is to decide a motion along the trajectory given by the curve. Okay? And of course, when you have a curve, you have a choice. You have basically two possibilities. You can run through the curve in one sense like that, or you can decide to go like that. So conventionally, one of these two ways of going through the curve is called positive, and the other one is called negative. There is nothing good in being positive or bad in being negative. It's just a matter of names. Okay? So, and what is the correct definition? So, very roughly speaking, the positive orientation of the curve is this one, when you are going counterclockwise. But sometimes you have a very, very bad closed curve. For instance, you may imagine a curve which is extremely strange, something. So I don't want curves that intersect themselves, but you can do something extremely, extremely complicated and then going like that and so on and so on and so on. Okay, you have a curve like that, and then you pick a point, for instance, this point here. And then you ask yourself, okay, what is the correct way, the positive way of going clockwise or counterclockwise? This one or this one? It is very difficult to decide in such a situation. Okay? But you know, through the theory that we made, in particular the closed curve theorem, that there is an interior part of the curve and an external part of the curve. So this is, if I'm not wrong, this is the interior. Yes, I think I made it right. So this is the interior part. So I don't want to color it in a very precise way as before. This is the interior. And the external part of the curve is this one. Maybe a bit larger, okay. This is the external part. So and a more precise notion of going positive or negatively, so clockwise or counterclockwise is positive, is the following. When you are running through the curve, for instance, you are here, then if you are running positively, the internal part of the curve is at your left. So for instance, you can imagine yourself going here. To be more precise, you go there by bike. I know that bike is becoming popular in Uzbekistan now, very good. So you have a bike, or if you prefer a motorbike, but bike is more ecological, it's much better, okay. And then, if you want to know whether you are going positively or negative, you just take your left hand and stretch it. If when stretching it you are inside, in the inside region, then you are going positively. And this is the correct direction. Positive orientation. Okay? Of course, notice that there are points in which, if you want to use this way of using a bike and then stretching the left-hand side, this one's left-hand side, you don't have to stretch it too much, because here the width of the internal region is very small. Okay? This is sort of fun. You just put a bit your left hand, okay? And then what you have to meet is the internal part, and you are going positively. Okay, this picture is quite complicated, but in the first picture you see it much better. So you are here. For instance, you are going here, and you put your left hand side there, And of course, you are with your left hand side outside the curve, so you are in the external region, and